solubility products. So this is about KSP. What exactly is KSP? You can see that KSP is really another constant. So KSP, and what the KSP stands for is solubility product. So what this represents is basically anytime, again, you see K, this is at, well, that's at equilibrium. What solubility product is, basically what it means is, does your compound, will it dissolve well? So basically, will it dissolve well? Some products, some solid compounds will dissolve completely very easily, such as like your table salt, whereas some other compounds, such as like the first one, aluminum hydroxide, will not dissolve it as well. So to give you an idea what KSP, where the KSP value is from, let's make sense out of this. How you want to write this is that KSP is another one of those law of mass action, sort of a very similar expression. So if we were to use the first one, aluminum hydroxide, this is aluminum hydroxide. If this were to be dissociated, you would have Al3 plus 3OH negative. All these are aqueous, right? So then where KSP is from, KSP is the same as your other K, except that, oh, I'm changing my view here, except that for KSP, you're not going to include your reactant because that's your solid. So instead of having your product over your reactants, you're actually just going to have your product. So this is Al3 plus times OH, and then this is to the power 3 because this molar coefficient will become your exponent. So this is where the number is from. So if we were to take a look at the KSP value of aluminum hydroxide, which is 5.0 times 10 to the negative 33, so ask yourself, in order to get this number, what kind of numbers do these ones have to be? Are they going to be large numbers or small numbers? So you can see that since this KSP is an extremely small number, this is times 10 to the negative 33, that means these numbers must be very, very small. So these ones are going to be incredibly small number, and what that means to have small number is that your small numbers basically means that these ions will not really appear because they have such a small concentration of it. So if you have a small KSP like this one, times 10 to 33 minus 33, that means that these ions have to be very small. That means that it does not dissolve that well. That means that this aluminum hydroxide in solution will not dissolve that well in water. If you compare that to, say, something like lead chloride. If we were to take lead chloride and dissolve it in water, this would actually get a lot more ions of lead and chlorine, a lot more than the concentration of aluminum hydroxide. So that's what KSP represents. So this is KSP, this is at equilibrium. The next video that you will see about predicting if a precipitate will form, that is something called QSP. No, it's not SP, this is at equilibrium. So that's the two things. So let's move on to an example here. So the first one is calculate the solubility product of AgBr. So solubility product, that's your KSP. You want to calculate AgBr. Let's write AgBr, and then let's write the dissociation. So this is going to be Ag plus. So it breaks it down into this, and then this is your Br. This is going to be Aq. So then we're given 6.7, this is 6.7 grams times 10 to the negative 5 grams of AgBr, and this is in 500 milliliters of solution. So the first thing you need to do is you have to change all of this stuff into molarity if you're not given that. So 6.7 times 10 to the negative 5 grams of AgBr times, and then grams per mole, and then here we need to calculate the molar mass of Ag and Br. So what's the molar mass of Ag and Br? Let me see if I can have a periodic table. So the molar mass for Ag is 107.87 and bromine is 79.90. So the total molar mass of silver bromide is 187.77. So 187.77. So this will just change into moles. You can see that it's just another step in your molar conversion. So this is, the answer here is 3.56 times 10 to the 1, 2, 3, 4, 5, 6, 7 minus 7 moles. This is not done yet because we have to change this into our molarity, so we need to divide this by 0.5 liters, not in milliliters but liters. So this is going to be divided by 0.5, giving me an answer of 7.13 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, negative 7 molarity. So what we just calculated is basically this is the concentration of AgBr. So this is at AgBr at equilibrium. So how do we calculate the entire KSP? So let's go and move down a little bit. So remember, KSP is going to be my ion concentration, my silver, and multiply that to bromine, but we don't have any of these concentrations yet. So if we were to look at this, where do we get the concentration of my ion concentration? So since we calculated this molarity, this represents the concentration of AgBr, right? So then that means that if we were to look at the equation, AgBr, this is 7.13 times 10 to the negative 7. And this will dissociate into my Ag plus and Br minus. Since they're 1-to-1 ratio, that means that this is going to be the same here. This is going to be the same for bromine. So we can plug this concentration back in here. So basically is just 7.13 times 10 to the negative 7 times another one. 7.13 times 10 to the negative 7. And then multiply all this. That is your answer. So you should get an answer of 5.09 times 10 to the negative 13. That is your KSP, no units. That's your KSP of your silver bromide. So that's your first example. Next example is, let's see this. A saturated solution of calcium hydroxide has an hydroxide ion concentration of this. Calculate the KSP. So first thing you want to know that is that in a saturated solution, this is the maximum amount of solute you can have in a solution. That means that you dissolve all your solid and then the solution cannot hold any more solute. So it cannot hold any more calcium hydroxide. So that's what a saturated solution represents, the maximum amount. So let's start just by writing this balance equilibrium expression or reaction. So Ca2 plus 2OH minus. So then saturated solution of calcium hydroxide has a hydroxyl ion concentration. So this is 3.0 times 10 to the negative 3. So then I need to calculate the KSP. So KSP is basically just going to be my Ca2 plus, and then this is going to be my OH minus squared. So then I need to calculate the concentration of Ca. And we're going to use a molar ratio. So this is 2 times as much as calcium. So that this is going to be 1 or half as much. So this is going to be 1.5 times 10 to the negative 3. So just plug in these numbers, times 10 to the negative 3, times 3 times 10 to the negative 3. But now I need to square. This gives me a final answer. Let's see, 3 to the power of negative 3 square times 1.5, 3. This is going to give me an answer of 1.3 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Negative 8. So that's my KSP. So this is negative 8. So that's the KSP of calcium hydroxide. So how well will this dissolve? So you can see it's a pretty small number. It doesn't dissolve that well. Next example. That's all the examples. Okay, so hopefully these three has helped you understand solubility products. So let's catch you next time. Thanks for watching.